So let us now approach another concept of another solution concept, another concept of what is a stable state, a concept which will be called rationalizable strategies. And of course, that's a concept which we will see how it is related to what we already know. But let us start with the notice that Nash equilibria require basically each player to best respond to a correct belief. So first of all, it has to be a best response. Second, it has to so maximizing the player's utility. Second, the belief about the others that the player uses when calculating what would maximize her utility should be correct. So every player plays something optimum, and the rest play the optimum with respect to what the others actually play. Now, of course, this knowledge is maybe natural in repeated plays where you can gain some experience, but for a one-shot play, this epistemic assumption is quite strong. Epistemic refers to epistemology, which is what we know. So we don't typically, or at least not always, know what others are doing. We actually emphasize that they're doing it in the same time. So when you have, for example, paper, scissors, stone, paper, scissors, or matching pennies, we always have to take into account that for this strategy of the other player, we need to play this. For the other strategy, we need to play something else. So this belief is too strong. And what rationalizability does is that it only assumes that we rationally best respond. We do just best is what we can do best, but the belief can be any belief, which in turn assumes that the others are also rational, and they assume that others are rational, and they assume that that others are rational, and so on. So that goes indefinitely deep. So we are rational in the sense that we best respond to the belief we have, and the belief itself is that the others, what they do is better, is the best for them, and they think that the others do the best for them, and so on. So we only have this rational grain left, so it's weaker than Nash equilibrium, but more realistic. And of course, in reality, this can also be challenged because this idea of a theory of mind, which is a name for what I think that someone else thinks, and so on, it usually goes in real people. It usually depends on the situation, but it does not go beyond like 3 or 4. So it's also too strong. It's not like infinite, but at least it's more realistic. So at least for people who are infinitely rational, it works. They don't need to be also omniscient. They don't also know. They don't have to know everything. So in that sense, it's more realistic. And of course, the question is basically, what does this indefinitely nested theory of mind give us? What does it give this assumption? So basically, now we're going to dive a little bit to this epistemic game theory. That's not what people usually do on a basic game theory course, but it's good that we know you have a taste of that. And what we will do is that it means that we explicitly consider beliefs, which we need to think of when we talk about Nash equilibria, but then we did not explicitly define beliefs and so on. Another thing, in addition to this new solution concept, which is, as we see now, it's clearly just a generalization, a weakening of the Nash equilibrium. It also is going to relate to this iterative elimination of strictly dominated strategies and help us prove that this iterative elimination of strictly dominated strategy, for example, eventually the result does not depend on the order of elimination. So it will be related to this. So that's also related to what we do now. And now let us go further. So let us define what a belief is. A belief is simply the following. A belief of player I is the probability measure on the other player strategy. So my belief is what I think is reasonable, what is probable, quantitative, I suppose, what is the probability of each strategy profile for the others. Now, they may be dependent. I may believe that they either do this together or that together. If, let's say, there are 3 people, I can say that either the 2 other guys go together to a pub or they go together to the theater. But it's not like I only have to independently say what I believe about each one of them. If we do require independence, that would actually yield other results than what we have here. So that would actually change the result. So it's important to notice that here the belief about the others, they can be any beliefs, including those which are independent. And being rational means that you best respond to your belief about the other. So from all the strategies you have, you choose a maximum. Well, of course, you assume that a maximum when it exists, which usually is the case. So let us define what we mean by rationalizability. And first, we start with the basic things. So given a game, a strategic game, usually we are going to assume it's finite. Players and strategies S, which basically S is the Cartesian product of S1, S2, and so on in Sn, and utility functions, as usual. Now, a strategy Si of player I is called rationalizable if all of the following exist, and we are going actually to continue the definition, but let's start with those 3 things we need. T denotes the depth of the intuition. So now I'm going to explain you the intuition. The intuition is what I just explained, that you believe that the other person is rational and the other person thinks that the other people let me start again. Each of the other players is rational. You believe that each of the other players thinks that each of the other players for that person is rational and thinks that each of the other players is rational, and so on ad infinitum. So that's basically the belief, the requirement of the beliefs you have on those probabilities, and given that requirement, all the things which can be optimum given that are fine. So there is no need to actually to have a consistency of any other sort here. That's the basic idea. Now we need to write it down, and that's clearly not so simple. When we say like that and that believes that and that believes in that and so on as infinitum, that's clearly not simple, but that's not so hard either. Let me explain you the definition. So given a game, Si is rationalizable if all of the following exist. First, sequence of sets. Now those are sets of strategies which we need to assume other people may take in order to rationalize some of our strategies. So for each one of those depths T, and for each one of the players J, xjt is the strategy set of players J in time T. So of course it's always in Sj for any player and for all those times from 1 to infinity. So while times are 1 and times are indexed by natural numbers which are from 1. Now those are sets of strategies we need. Now I believe mu ji. So above we have the t here and I1 also is the first time. So player I, whose strategy is I, we call rationalizable, has a belief ui, below is the index of the player, above is the time, such that if there is some sort of subprofile of the other players which is in the support of ui, so ui 1 because it's the first time. So that's what actually directly has to justify Si. the first level of indirection, we say. So if there is mu I1, if it believes that others can play something with a positive probability, that something has to be in that X. So X is the set of strategies which we need in that way. Now, okay, so later we are going to tell that given that mu as I has to be a best response. Now, but we need other sets as well, other beliefs as well, a set here. Why do we need other beliefs? Because in order to justify what we have here in x1 minus I, we may need some other actions of other players such that based on the beliefs which will justify those actions. And formally, for any player and for any t larger than 1, if you have some action of some player j at some time t, as j in xjt, then there exists a belief which depends on that as j. It's not what the belief gives as j, it's a belief which depends on that as j. So a belief of player j, which is required to justify as j. I think the notation here can be improved, but in this case, it's not that it's a function which gets as j, but it's rather a belief which is parameterized, we may say, required to justify j. It's a belief about what happens in the next step, because you always justify by a deeper layer, or the next deeper layer. And if that belief, now it's actually an input. So the belief is also about the strategies of others. If that belief believes that the others can play something with a positive probability, then that something has to be in that x minus of the others in the next time. So basically, we have this belief which justifies SSI. Now that belief is about some strategies of the first step in x1 minus I. And those strategies in turn, and strategies in any depth, need to be justified by a belief about the next step, about some strategies in x of the next step. So basically, beliefs here, in general, beliefs first justify, they justify as I. Those are beliefs of depth 1, and then those beliefs believe that the other players play something, and that needs to be justified by the beliefs of the first depth, and so on. So exactly what I said, that I believe something, those are beliefs of order 1. I am optimum with respect to them. That's that. I will now tell the more definition. Now that thing believes that someone may play some s minus I, and then all those s minus i's which I may need for justifying what I have, as mentioned t is 1 here, they in turn need to be justified by the beliefs of those players of what players do on the next step. So then those what have in the second step needs to be justified by beliefs for the next step, and so on. And the sets of strategies which may be in the support of those beliefs, which are the strategies we're talking about, is this XTJ. Okay, so those are the necessary things to have. Let me actually change the parentheses. I think that it can be confusing. So I've changed the notation a little bit. The thing is that, one second. Now the thing is that in the book, but in the Osborne and Rubinstein book, which I follow here, they don't actually notify directly what is the probability of something. They just notify probabilities as functions of what they need to justify. So, for example, mu at the next depth level at t plus 1 of j, which justifies as j. And this is defined by normal parentheses, by circular parameters. But if I want to say that the probability it ascribes to something is such and such, so for example here mu1 of I is given s minus I, positive probability, then they don't directly write that. Now I do want to write it sometimes, so in order to be consistent with the book, which allows you to easily, if you want, to easily read the book and understand it, I actually use the same notation here. So I don't like it much, but the notation is that if the probability is simply parameterized by something, so the probability distribution which is used, which allows Sj to be best response, then I use circular parentheses. But if I want to say the value that the probability value that the probability function ascribes to someone, then I use just a square bracket like here. So it's the probability parameterized by Sj, the probability which justifies Sj, and usually it justifies a single action, a single player, pure action. Now, the domain where it acts on is the strategies of all the others. So it acts on the S minus I. That's all this. That is going to be the strategies of all others. That's also something you can do. So okay, let us now go to the definition in full. Let the definition in full. So first, let's just recall what we just said. So you have a rationalizable as pure strategy if there are those strategy sets simply which contain the strategies which, because they contain the strategies which we need in order to justify them. Basically, if the belief justifies, we'll see later that it justifies, Si assumes that some S minus I has a positive probability, it's in support, in other words, that has to, then S minus I has to belong to that xy, x1 minus I. And if at some level of indirection, there is some strategy which is justified by some belief, then all that in support of that belief has to belong to the next level of, to the next x. So x's contain all those necessary strategies for the justification, and beliefs, they are those beliefs which allow justifying. Now what does it mean? Okay, that means the following. So such that I, that is the strategy which we now, which rationalizability we are now defining, Si is a best response, not necessarily the only, but a best response to U I at the first level of indirection. So it's the best response. That's justified by that. Now, x I1 is 0 because mu I1 only looks at the others, and for each player which is not I, x I1 contains those who belong to something which is in the support of mu. So in other words, x1 are those we need for mu1. We don't have to say it, but we can use it. We can add this. Now, part 3. For any excuse me, for any player and for any level of any depth t, if there is Sj, so some action of that player in xtj, it needs to be justified. So we start with mu 1 justifying as I, but it needs some actions, and those need to be justified, which also need some action, and that needs to be justified, and so on and so forth. Theoretically, it never ends. So for any player, for any depth, and for any action of that thing in that xjt, xj is the best response to the belief about the next step, which is used to justify xj. And again, we say something we don't have to say, but it allows us to kind of simply write what we need. So the axis of depth T for J are exactly those. There is some player other than J and some action of that player, which in order to be justified uses belief mu as K, such that in its support it has some S minus K, which has Sj prime. So again, at some point we need that. So we basically axes are those we always need. You don't have to say it because axis will include everything we need. We already said this in the beginning. And it will not include anything else because anything else will also have to be justified. So, well, okay, if you want, you can add something else, but the necessary things you need to fulfill in order for an action to be rationalizable, and that is just remind that that's what we are defining, is that there are some axes which contain exactly what we need. They may contain more, but they contain exactly what we need for the belief to justify SSI. And those which are contained in x1 need some other belief, some belief to justify them, and that requires the next actions to be contained in x of the next step, and so on. So basically, we have just written down what we said in the beginning about that. I just, not I like index, but I myself, that I just said that we have a sequence of justification. So I am rationalizable if an action is rationalizable if there is a belief such that action is a best response. Now, everything which is in the support of that belief belongs to this set, which we just use for notation X. Everything which is in such a set has a belief which rationalizes it, and that belief, now we go further and further and further. So, okay. Now, as condition 4 and 2 and 4 are superfluous, so here I denote them by a frame. Now, it's simply nice for the definition. And now let us look at a simple example. So let us look at the action Si. And in order to be justified, it has needs some belief about the actions of the others. So x1j and x by k. There are three players I, j, and k. Now, x1i is empty. There is no need. There is the belief of player I about the others. It does not believe anything about itself. Now, as to the other set, they are not empty because the belief does have something in its support, right? Because the total belief, the total probability always sums up to 1. So it's not empty, and those need to be justified, so they have to believe something. For example, everything xj1, if I read from first the lower index and then the upper index, everything xj1 has to be a best response to something, some distribution which has its support in xi2 and xk2. And about everything xk1 is the best response to a distribution which has some distribution which has support in xj2 and xk2. So they are not empty. And that's always true if n is at least 3. But if n is 2, there are 2 players, then we always have that one of those sets is empty, simply because. Why? Because Si is justified by a belief about xj, and there is nothing we need in xi1. But in xj1, whatever we need is now justified in turn by a belief about xi. So we need something here in xi2. But we don't need anything in xj2, and so on. So those sets are intermittently, one of them is empty. The xi on the depth to t minus 1. So in all depths is empty, and xj will be the emptied even then. But it's only if there are two players. If there are at least three players, then only xi1 is empty. So the meaning of, as I said already, xji in general for j which is not I is the set of actions that I believe j can undertake to justify si. Similarly, on the second depth, the set of actions, the xj2 is the set of actions that of j such that there is someone, some k which is not j, and there is some action of that k such that it's the best response to a belief mu k2 of sk, and that belief, well, it actually not only looks at the j, it looks at everyone who is not k, so it's I and j, but you can say that the marginal probability of both j is not zero. So as j appears in something which is not a zero probability, in some pair of action. So that's what I mean by this notation. UK2 of Sj is possible. Okay, now let us look at an example. This is a definition which is not hard, but it's extremely kind of convoluted with that notation. So let us look at an example. So consider an example, and again, that example is from the book. Most, I think, virtually all this chapter is about rationalizability. Besides the way I present it, it's everything from the Osborne and Rubinstein. So consider the game on three players with the same strategies A and B for both players, and assume that strategy A is rationalizable by, so it's the best response, given a probability distribution uy1, which is support AA and BB. So about it has let me see. So it has a non-zero probability for the other players playing A and A, and it has a non-zero probability for the other players playing B and B. Please take a note that according to this, that it's the only things in the support. These are the only strategy profiles in the support. U11 believes that the probability that the other players, so player 2 and 3, play A and B together, that's zero. They only can play something that either both A or both B. Only we can play the same thing. That's what we write here. So that's definitely a dependent probability. And by the definition of X, so the X's of 2 and 3 have to be both A and B. Now the beliefs of for the second depth, so in order to justify A and B in x21 and x31 with the beliefs mu, so the beliefs justifies A in x21 is called mu to A, and the beliefs justifies B for the belief of player 2 justifies B in x21. So those two actions in player 2 and the beliefs to justify them are called mu2 to A and mu2 to B respectively. What does it mean that they justify them? That A is a best response to the belief mu2 to A, and B is the best response to the belief mu2 to B. There are distributions on S1 and S2. On the other players, for player 2, it's the S1 and S2. Now, they are not necessarily independent distributions, as I already have emphasized several times, and similarly, for player 3, the beliefs to justify A and B are called mu32a and mu32b. And the fact that they justify what it means, the fact that they justify those actions means that A is a best response. For B, it's the best response from the point of view of repli of player 3 from U3 to A. And B is the best response from the point of view of player 3 for mu3 to B. And those are distributions on the other players from the point of view of player 2, player 3, and those other players from the point of view of player 3 are S1 and S2. Now, note that those distributions don't have to coincide on what they predict player 1 will do. They also don't have to contain A as one section in the support. They don't have to ascribe a positive probability to A being played, despite that we start with A's rationalizability. So there is no need to be consistent. You just need that I believe that that something is consistent. It's the best response to what I believe about others, and they best respond. What I believe about them is the best response to what they believe about the others, and it's the best response about what they believe about others, and so on. There is no need to have a consistent structure. Now X, so on the second depth, the X of player 1, on the first depth, I remind you, it was empty because our belief was only of player 1 itself, himself or herself, and the belief of player 1 is always about the other players. But on the second depth, it's all the strategies of player 1, such that at least one of the other of those distributions would justify the strategies of other players. So mu22a, mu22b, mu32a, and mu32b. Assign it a positive probability. Now, for other utility functions, the sets may differ because the sets depend on the utility functions, because they are what we need, the strategy which are the support of the distributions, which are such that will make some actions the best responses, and that depends, of course, on the utility function. So the sets xit may differ, but only xi1 will be empty. It's empty because the only belief which is relevant at the depth is what player 1 believes, and the belief goes about the other player. So there is nothing about player 1 itself. And from that point on, there is all this something which requires any player to do something. So there is no empty x of any player, I or any other player at any depth beyond 1. Now there is another much more simple definition of rationalizability, which kind of looks at one step. So instead of saying I do something which is justified by what the others do, and that is justified in turn by what the others could do, and that is justified in turn by what, so on and so forth, indefinitely long, we can define, and it will show it the same, a game which is, in a way, you can say it's recursively, circularly rationalizable. So given a game, strategist I is rationalizable if for any player, if for any player there is a subset of that player strategies. So for any player J, there is a subset ZJ of that player strategies. Second, it's recording. Okay, there is a subset of that player strategies such that Si, the thing we need to show it's rationalizable, is in the die. And in general, what does mean that all those are rationalizable? Those strategies justify one another. So for any Sj, J can be I or not. In Zj, there is some mu J based which justifies that in a way. That Sj is the best response for that. And anything which is in the support of that belongs to the others J. So you can only justify whatever you have, yes, given a belief which has its support in the others, which in turn are justified by what have its support in the others. And the remark is actually interesting that, so first of all, notice that if you have a set, a sequence of sets, the J indexed by the rational by the nature numbers, and you have another sequence, the J prime, indexed by natural numbers. When I say natural here, I mean from 1 and on, so not including 0. Of course, I could just start with 0, whatever. Just that that's the convention here. So if you have two such sets which satisfy both those two conditions, in other words, that those strategies which are in those sets are rationalizable, so does the sequence which takes at each which takes for each player the union of those z. So it takes the jet united with the jet prime. And therefore, the rationalizable profile can be defined as the largest such Cartesian product of such z's, which satisfies this definition. Now let me unpack. It's not hard, but just let me unpack. So first, if you have indeed two such z's, you can always speak about a union, and that will always satisfy the definition. Why? Because if everything in Zj is justified by some belief which has its support in Z minus J, and that is true for Zj and for the Zj prime, then everything in the union of Zj and Zj prime, it in the union means that it's in one of them. So it has, by what we already assumed, it has a belief. It's a best response to a belief which has its support in depends. If it was from Zj, it has its support in Z minus J. If it was taken from Zj prime, it has its support in Z minus J prime. But eventually, it has its support in some it has support in the union of Zj and Zj prime. So we have just shown that if there are two sequences or two n tuples, each of which satisfies what we need, here is no sequence n tuples. And then, so that's the n tuple which is made by member-wise unions. So Z. So Z is united with Zj prime. Now, therefore, the rationalizable profiles can be seen as the largest n tuple which satisfies those definitions. Now, it's clear that the largest n tuple, any n tuple which satisfies those definitions, is consistent by definition of only rationalizable profiles. Now, on the other hand, if anything is rationalizable, it has to be in that n tuple, because if it's rationalizable, there is some n tuple which fits the definition and justifies the rationalizability of the profile, and then we can just unite it with the existence if it's not there yet. So therefore, we've just proven that the set of all rationalizable profiles can be defined if it's defined as the set of all profiles which satisfy the definition, it can be also seen as, or it is the same as the largest Cartesian product of those, the J satisfy they satisfy the definition. So it's simply another formulation of the second definition. And now the interesting important probability is, of course, that the two definitions are equivalent.